Thank you. Can you hear me? Okay, I think so. All right. I'm really excited to be here with you all today to discuss my vision for the next half century to century of collider physics. And today I want to start off by asking a question that Ernest Rutherford also once asked in 1906. What is the smallest stuff like? And that's a direct quote, by the way. I'm just kidding. So at the time, the general consensus view of atomic matter was the so-called plum pudding model of the atom. We knew that the electron existed, so we knew that there could be free electric charge, and we knew that matter was neutral, that the positive and negative charges had to somehow balance out together. And so people assumed that these negative charges, these electrons, were somehow embedded in some jiggly, amorphous blob of positively charged stuff. And Ernest Rutherford went out to test this. And he did so with his famous gold foil experiment, where he took a very thin layer of gold foil, as you can imagine, and bombarded it with a radioactive source of particles. And if the plum pudding model were correct, particles he's bombarding it with would kind of just pass through. But he found something really surprising, in that most of these particles passed through, but some of them scattered at these really high angles, indicating that atomic matter is mostly made up of nothing, and then once in a while you get something super dense that can create this really hard scattering process, and that is what we call the nucleus of an atom. And that, in fact, is a more correct description of atomic matter than the plum pudding model. And so this paper he published in 1911 established this nuclear model of an atom. And so later in his life, Ernest Rutherford asked, or asserted, that higher energy particle beams to bombard matter would open up an extraordinarily new field of investigation. Indeed, when he bombarded atoms with a radioactive source, the particles were kind of bouncing off nuclei. But if you can really punch energy into those particles, you can start to kind of get at the finer structure of the nucleus. And if you can get an even higher energy, you can even start to probe the substructure of the nucleus, protons, neutrons, quarks, etc. And so the point I want to convey here is that the higher energy you go, the tinier scales, the smaller scales you can access. So that's kind of a theme of particle physics. We want to push to higher energies and access the tiniest, more fundamental things. Okay, so how do we actually go about accelerating particles and doing, following through with his vision of making more energetic particle beams? Well, first we have to accelerate charged particles, and we do that with electric fields. You all may be familiar and have created electric fields at your homes, at your birthday parties, by rubbing a balloon on your head. What happens is the balloon is absorbing all the electrons out of your hair, and what's left is overwhelmingly positive charge in your hair. We know like charges repel, and so your hair kind of sticks out. It doesn't like to clump together. It likes to stick out. Those positive charges want to repel. And so we can do basically the same thing with particle physics, where we can put a bunch of positive charges on one side, a bunch of negative charges on another side, and if we put something that is also charged in the middle, here we have a positive charge, the positive charges are going to want to repel it, they're going to want to push it, and the negative charges are going to want to pull it. And so we can do this, obviously, in slightly more sophisticated ways to accelerate particles to higher energies. Okay, now once we accelerate particles, we want to control them. We just don't just want to accelerate them randomly. We want to be able to actually control what we accelerate. And we do that with magnetic fields. And we know from examples of, say, the Earth's magnetic field that charged particles bend in the presence of magnetic field, and this is actually what is responsible for creating the aurora borealis. We have charged particles coming from the sun, passing through the Earth, and somehow they get basically deflected by the Earth's magnetic field, and they come to Earth, and we see these beautiful sights. I haven't seen one, but one day I hope to. So as an example, here we have, imagine a magnetic field is coming out of the page. If we have a positively charged particle entering that magnetic field, it will bend, and it will bend to the right. And if it has a higher energy, it's going to bend less. If it has a lower energy or lower momentum, it's going to bend more. and we can control particles with magnetic fields in this way. Okay, so one of the first ways that technologies that we actually implemented to actually produce these higher energy particle beams in controlled ways is something called a cyclotron, where we have a radioactive source that gets bent in magnetic fields in this kind of circle, in this cycle, if you will. And every time it passes through one of these red arrows, it gets kicked with a little electric field. And so it's accelerated in this circle, and then you get a high energy beam that you smash against the target, just like Rutherford had imagined. And the first cyclotron was invented in 1929 by Ernest Lawrence. It's, just for the record, that iPhone is to scale. So this machine could basically fit in the palm of your hand. And it reached an energy of what we call 80,000 electron volts. So 80 kiloelectron volts. That, you don't need to remember that number, but it's about to get a lot bigger. So you can kind of track how much bigger that will get. And so as this technology kind of percolated throughout the world, people started building bigger and bigger and bigger cyclotrons, including here at Nevis. In fact, in 1950, Nevis, the building right over there, hosted, turned on, at the time, the largest and most powerful cyclotron. And at the time, now President, then General Dwight Eisenhower was the one who actually flipped the switch and turned it on. A little fun piece of history. I think it's really funny that in one of the news articles, there's a little quote that says, "Works perfectly." So I kind of highlighted that. But this cyclotron, made some incredible scientific discoveries, achieved energies of 400 million electron volts. So now we're going up from thousands to hundreds of millions. There's some really nice photos that Bill shared with me of the construction of the cyclotron, and you can see how much bigger it has to be. You have a person in there to actually achieve these leaps in energy. So the higher energy we want to go, the larger machines we have to build. So you can see a little fun fact I also learned about the cyclotron is you'll see these circle windows up here, and that's because part of the funding came from the US Navy, and these are decommissioned battleship windows, which is kind of fun, and was the only thing that actually lets in light when something like a power failure happens and you lose all your electricity. But anyway, I just want to highlight, the scale of this, and also point out, everything I'm about to talk to you about these larger and larger machines, this broad vision, is really built off the machine and the physics and the science that was done here in our backyard, which is really nice. Okay, so people kept building and imagining bigger and bigger and bigger and bigger machines. And to the point where, at one point in 1954, a famous physicist named Enrico Fermi said, okay, it was a bit of a tongue-in-cheek proposal. If we're just going to get bigger and bigger and bigger, one day we're going to build a globotron, and we're going to have a cyclotron that's really just wrapping around the Earth. He didn't really intend for this to be an actual machine. It was kind of a pithy comment. But ultimately, what he proposed was something that could be built 40 years in the future, so in 1994. It would be 40,000 kilometers, and it would reach 3 trillion electron volts, or 3 TeV. So we went from tens of thousands to hundreds of millions to trillions. Okay. So I want to highlight now a couple limitations of this, and how we can use some paradigm shifts, how paradigm shifts in the field of accelerator physics and particle physics basically meant that we, obviously didn't end up building this, right? So the first major limitation is that this globotron was a fixed target machine. That means we had this very, very powerful particle beam smash against a target. At the time, particle colliders had not been invented yet. So actually, it's a lot better to smash 2 particle beams moving against each other than to just smash 1 particle beam against a target. So this represents a significant paradigm shift, and you might be wondering, why didn't Fermi think we could smash particles together? And it's because it's really, 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 really hard. As an analogy, if the width of a human hair were the width of an Earth, the Earth, a proton would be the size of a grain of salt. Just to give you a sense of scale of how freaking tiny protons are, and yet somehow we are able to collide these control and collide these particles together. It's really an incredible human achievement. Okay, back to the Fermi's Globotron, which again wanted to achieve 3 trillion electron volts in 1994 with a 40,000 kilometer tunnel war. It might surprise you to know we almost achieved this. We got about halfway there, 1.6 trillion electron volts. In 1985, so 31 years, so less than 40 years, in a tunnel that was only 6.2 kilometers. So like around 10,000 times smaller than what Fermi had initially hypothesized or proposed. And this is because indeed we were able to collide particles. We figured out the technology to collide particles together. So really this paradigm shift, but also we had new technology. At the time that Fermi proposed this, we didn't have superconducting magnets. At the time of the Tevatron, we did, so that enabled us to bend particles a lot better. Okay, so that those superconducting magnets and the paradigm of colliding particles also extends to the Large Hadron Collider, which is, as I think many of us know, the largest and most powerful particle collider ever built by man. It is located at the Franco-Swiss border, right outside Geneva, Switzerland. It's 27 kilometers circumference, or 17 miles, since we're in the US. And just something I like to point out is this is the Geneva airport for scale. A little to the right of the flag's icon, you can kind of make out the airport just to give you a sense of how vast this machine is. So we collide particles 40 million times per second, and then the places where we have these particles smash into each other, we put these giant particle detectors. There's 4 different collision points where we put these detectors. I'm mainly going to focus on 2 of them, which are kind of the general purpose experiments. The others 2 are a little more specialized. But one of them is the ATLAS experiment, which is one of the experiments that Columbia is a member of that I did my PhD on. And the other, at the other side of the ring, on maybe potentially what some would say the dark side, is the CMS experiment, which is where I currently work as a postdoc. And to give you a sense of scale of these experiments, at the ends of these teal turquoise arrows, you can see people figures. So these are like several stories high. The length of these is like half of a football field. These are truly vast machines. But to get to the, okay, so how does the LHC actually work? Well, we don't just inject protons and go from 0 to 13 trillion electron volts. We start by passing protons through smaller facilities that once were colliders in their own right. So we go through these earlier stages, and then those are used to inject the particle beam into the LHC, into the Large Hadron Collider. So here you kind of can see these magnets, by the way, in the LHC are indeed blue. And we're about to go into the beamline and see this proton with the 3 quarks inside zooming along at almost the speed of light. And one is approaching from this side, from the right, and another is approaching from the left. And inside of this massive detector, they will collide. All right. And we see a stream of particles. This is a Higgs boson candidate event. So you can see the Higgs boson was produced in the middle and decayed to 2 photons, which are in the green kind of energy depositions in the detector. So I know that this lecture is really focusing on colliders and the future of colliders, but as someone who works on these detectors and work on these analyses, I want to spend a brief time explaining what the heck we do with these collision products in the first place. Okay. So this is little white dot. You can imagine as the proton beam coming out of and going into the page. So I'm going to build off of that. So the closest piece of our subdetector that's closest to the beamline we call the tracker. And the tracker is responsible for tracking the paths of charged particles present in a magnetic field. So we know that charged particles bend in the presence of a magnetic field. they leave these particles, charged particles that bend, leave hits in our tracker, and we can basically use the trajectory of these hits to reconstruct particle tracks, so the trajectories of these particles. After the tracker, we have the calorimeter system, which is responsible for measuring the energies of particles by stopping them in the calorimeter. So in green, we have the electromagnetic calorimeter. This is responsible for measuring the energies of electromagnetic particles like photons and electrons. And this is where the Columbia Atlas group has played a major role in the Atlas electromagnetic calorimeter electronics. And then after the green, we have the blue, which is the hadronic calorimeter, which measures the energies of hadrons, or things that are made up of quarks. So we basically can look at these energy depositions, cluster all of these different energy depositions together using algorithms, and then use integrated information across the tracker and the different calorimeters to reconstruct particles and perform particle identification. So for example, something like a photon and an electron both leave a similar signature in the calorimeter, but a photon is neutral, so it doesn't leave a track in the tracker, whereas an electron is charged, so it does leave a track in the tracker. So this, you don't need to remember all of this, but this is, this is a lot of, when you're wondering what we do all day, a lot of it is this. And then finally, outside the calorimeters, we have the muon spectrometer, which is responsible for measuring the trajectories and momentum of muons, which is typically escape the calorimeter. Okay. So what do we actually use all of this information for? You might be wondering. Well, we use it to do a lot of things, including discover the Higgs boson. And a lot of the times people think, okay, you discovered the Higgs boson, what now? What else is there to do? Well, there's a lot to do, because after you discover something, you want to learn everything you can about it. We want to really characterize this particle. And so that's what a lot of the work at the LHC has been doing over the past decade or more since this Higgs boson discovery. These are like my only plots in the talk, I promise. I do want to explain them, but you don't need to worry, I won't show more plots, really. I won't show more plots like this. So okay, on the left plot, we have, we know, maybe we don't know, but I will tell you, the Higgs boson is really important because it's responsible for giving mass to particles. And so we want to double check and say, is the Higgs boson coupling to particles, is that actually proportional to the mass that we measure of that particle in other ways? And in fact, we find that they are very, very close. And so you can see here on the y-axis of the left plot, the coupling, and on the x-axis, the particle mass, and you'll see this linear relationship. And so that linear relationship shows that yes, it seems to appear that these relationships are one-to-one. On the right, what you can see is measurements, which are measured in these kind of white bars. And the dotted vertical line is the theoretical value. And so what we want to do is collect more data and perform better measurements so that we can make our error bars on these plots smaller and smaller and smaller, to the point where maybe we start to see a deviation between theory and experiment, and that's where potentially new physics can come in, and that's where there's a lot of work is going on here. Okay. In addition to the Higgs boson, though, there's a really broad search program. One of the exciting search programs at both Atlas and CMS, I won't go through all of these, but is the hunt for the particle nature of dark matter. There's a lot of different ways people are looking for it, and it's very extensive. And of course, there's much, much more. So this just shows a plot of, or kind of a diagram of different press releases of particle, of Atlas and CMS papers since 2015. And what you can see is that there's we're not slowing down at all. The number of the scientific output of these experiments is continuing to increase and increase. And Atlas and CMS, in fact, have generated nearly 3,000 publications together combined. And so, yeah, there's still a lot more science to do. Okay, so let's take a step back and think about what we've really accomplished so far in the field of collider physics. So this shows a timeline starting in kind of 1960, going past where we are in 2026 into 2040. And in blue, you can see particle discoveries with various types of colliders. And what you might notice is that the size of the particle rings, as we might imagine from what we learned earlier, kind of keep on getting bigger and bigger and bigger, culminating in the LHC. And so the LHC currently is only expected to run until the year 2040 or so. And so we are kind of at an important point in the field where we need to ask what is going to happen after the LHC. We're basically 14 years out of the LHC ending, and it takes a couple decades to even construct such a machine. So we need to be thinking about that now. So what really is next? What's going to happen after 2040? But before I talk about that, I think it's more important to ask the question, like, do we even need another collider? We already discovered the Higgs boson. Like, what's next? The standard model is, quote, complete. Ever since the standard model was theorized and formulated in the 1970s, every single particle, no more and no fewer, have been discovered, culminating in the discovery of the Higgs boson. So you might be thinking, okay, we're done, we did great, let's pat ourselves on the back, go on. But I'd like to remind you of a quote from British statistician George Box, which is, all models are wrong, but some are useful. Indeed, the standard model is an incredibly useful approximation of our reality. It is not perfect, and it's our job to figure out what is a better approximation, what is a better model of our reality. So what else is there that we have to study? What are we missing? And it turns out we're missing quite a lot. For example, we know from cosmological and astrophysical observation that dark matter, this elusive, invisible form of matter, permeates our universe. But we don't know what it's made out of at a particle level. We know that for some reason, our universe prefers matter over antimatter. And while there is a small degree of asymmetry between matter and antimatter in the standard model, it doesn't account for the vast difference, vast discrepancy that we observe where matter dominates over antimatter in our universe. We don't understand what's going on there. And furthermore, the standard model doesn't account for the gravitational interaction. It only accounts for 3 of the 4 known fundamental forces. And if we want to work towards a more fundamental theory of everything, we really need to start tackling these challenging questions. And I want to argue that we need to push to higher energies to do so. So one of the reasons that I want to push to higher energy scales that really excites me is the exploration of the unknown. I think this really sparks curiosity and excitement amongst people like yourselves who are taking time out of your evening to come to a science and physics talk. We're really excited about exploring the unknown and studying science for the sake of science. This is not an argument that always appeals to everyone. So in addition to the pursuit of knowledge and exploration of our cosmos, I want to argue, give us a more concrete argument of what we could really accomplish by pushing to higher energies. So this is a diagram on the left of the Higgs. We call this the Higgs potential. You don't need to really worry about what it is, but imagine that there's these fields that kind of have hills and valleys, like you've gone to the mountains and there's these hills and valleys and you can go up and down, and we really want to characterize the shape of that as it relates to the Higgs boson. In the standard model, it follows this green shape where you can see there's a fixed minimum right here at the bottom. And that means that this shape is stable. However, there could be new extensions to the standard model, physics beyond the standard model, that could change the shape of this potential, causing our universe to potentially be metastable or unstable, in which case we could quantum tunnel out of this green zone into this red zone, and all the matter that we know would not exist anymore, essentially. Okay, so we really want to characterize the shape of this Higgs potential. And currently, we've been able to measure it to a certain degree. We think theoretically it follows this white line, but we have a lot of uncertainty, a lot of error in these kind of brownish regions on the left. However, if we go to 10 times higher energy, we will be able to much more precisely measure this potential. So if it holds true to the standard model, we can measure it we can reduce all of this uncertainty to a very small level. And if it disagrees, we'll be able to identify that. So this is another argument that this is something that we know we concretely can do. And in order to get to this level, we need higher energies. And part of the reason why we need higher energies is because we need to produce events with multiple Higgs bosons in them. It's hard enough to produce just one, but we need events that have multiple. Okay, so how do we actually achieve higher energies? So the fundamental limitation, at least with a machine that's like the LHC, is that we are really limited by the magnet technology that is used to bend the protons in the collider. So if we had our magnets running as hard as they can, and we put more energy into the proton, we couldn't bend them enough. They would kind of have a larger arc, and we couldn't keep them in the collider ring. So that's really what is currently limiting us to pushing to higher energies. So in order to get to higher energies, we need a bigger ring and or combination with stronger magnets. So this is one of the approaches. This is the approach in particular that's being pursued by CERN, is to, okay, let's increase our ring by a factor of around 3, so going from 27 kilometers to 91 kilometers. And let's increase our magnets by a factor of 2, so going from 8 Tesla magnets, which already 8 Tesla is very high, to 16 Tesla magnets. All right. And so this is, again, as I mentioned, this is the plan for CERN. And this machine that is proposed is called the Future Circular Collider. And just as the LHC used previous collider experiments like the PS and the SPS as injectors into the ring, the LHC would become part of the injector to the Future Circular Collider. So what is the time scale of a machine like this? What is gonna, post LHC? So here we are in 2026. We have, until, as I mentioned, around 2040 of the LHC operating in between us now, and then also involves a major detector and collider upgrade that is in full swing. So the FCC is staged into two separate, fundamentally different colliders that use the same 91-kilometer tunnel. The first stage is what we call FCCEE. So this stands for Future Circular Collider Electron. This would be an electron-positron collider. And this is essentially would be what we call a Higgs factory. So we would be able to produce a ton of Higgs bosons, and we would really be able to nail down and better characterize the nature of the Higgs boson and the particles that the Higgs boson couples to. Later, decades later, the next stage after the FCCEE is the FCCHH. So HH, this stands for hadron, protons are hadrons. So this is basically the FCC with protons colliding at 10 times the energy than we currently have at the LHC. So while the Higgs factory is an excellent machine for characterizing the Higgs boson and performing critical measurements that we currently need, the next time, under this paradigm, under CERN's plan, the next time that we will be able to increase our energies beyond the LHC is around 2070 at the earliest. And that's kind of a long time. So let's take a step back and think about what particles can we actually collide. Let's start from let's start from step 0 and really think through how can we possibly get to this target maybe a little bit earlier, maybe in a little bit of a different way. Okay, so what can we actually collide? Well, we can collide electrons and positrons. We've been doing this for many, many decades. The pros of electrons and positrons is that since the electron is a fundamental particle, these produce very clean collisions. There's not a lot of backgrounds. Your measurements are super precise. The cons, however, is that electrons naturally, in physics, emit something called synchrotron radiation when they accelerate or when they bend. And this relation goes like 1 over the mass to the 4th. So basically the less massive a thing is, the more synchrotron radiation it will emit. So this really limits the energy reach you can do with electrons, because if you want to accelerate them any faster, they're just going to dump out that energy just as fast as you spent resources trying to put into the electron beam. Okay, so that's actually why we collide protons to reach higher energies, because we can't really do that with electrons. That's why the LHC is a proton-proton collider. Protons have the benefit of being more massive, so we can reach these higher energies. The synchrotron radiation is no longer the limiting factor. However, protons are composite. They're made up of quarks. That means that the energy scale of the physics you can do is far less than the energy of the beam. So what do I mean by that? I mean, we have a 13.6 trillion electron volt collider in the LHC, 13.6 TeV. But we're really only able to access physics at the TeV scale, at like a factor of 10 less than the energy we put into the beam. So it's not the most efficient way of accessing higher energy scales. Also, protons have relatively messy backgrounds compared to things like electrons and positrons, which have very clean collisions. So, can we think about a particle that is both fundamental, like an electron, and massive, like the proton? Well, I'm here to tell you, it is the muon. The muon is the heavy cousin of the electron. It's 200 times more massive than the electron, which means you get like a billion or 10 billion times suppressed synchrotron radiation, so that's no longer an issue. And because it's fundamental, we get relatively clean collisions, so we don't have the same messy backgrounds like we do with protons. The downside is, and the reason why we haven't tried to collide these particles yet, is because muons decay. They have a lifetime of a little over 2 microseconds, which is 2 millionths of a second. So, done. Luckily, for anyone who is an enthusiast of special relativity and time dilation and space contraction and all of this fun ways that time and space stretch and expand depending on your reference frame, I'm here to tell you that muon decays in 2 millionths of a second in its own reference frame, but in our lab's reference frame, it decays in just 0.1 seconds. So this is still very quick, but at the LHC, we're talking about 40 million collisions per second, so this 0.1 seconds is something we can work with. Okay, so what are some other benefits of a muon collider? Well, if we want to access energies 10 times higher than what we can do right now, a muon collider is around 5 times more compact than a proton collider that can achieve the same energies, and it's around 2 times more energy efficient than a proton collider that can achieve the same energies. And this energy efficiency thing, by the way, is something that is becoming increasingly of concern amidst various energy crises, etc. Another benefit that, in case I didn't stress it on the last slide, is that a muon collider offers a combination of precision measurements like electron-positron colliders and discovery potential energy reach of a proton-proton collider. So it's really a 2-in-1 collider. It's actually more like a 3-in-1, but we'll get to that later. Okay, so what does it actually look like? So the driving challenge in muon accelerator design is that, again, muons decay super quickly. So we just, you remember seeing the video of the LHC, we had these injector rings and they're going around and around, slowly ramping up. We can't do that. We need to accelerate them from 0 to 5 trillion electron volts in less than 0.1 seconds. So this is a big challenge. So I'll walk you through this cartoon accelerator complex. The first thing we need to do is we need to produce muons, because unlike protons and electrons, muons are not readily available. We need to make them. And we know how to make them, luckily, which is by taking a super intense beam of protons, smashing it against a material. It produces particles that we call pions, which are hadrons, so they contain 2 quarks. Protons and neutrons contain 3 quarks. These pions contain 2. And then the pions decay. The pions decay to muons and particles called neutrinos. In fact, for any of you who are neutrino enthusiasts, this is the same process that is used by the LBNF Dune project to study neutrinos. And a lot of this infrastructure is already at Fermilab outside Chicago. Okay, so once we've produced muons, we need to do what we call cool them. So what do I mean by that? When we produce muons, we have basically like we want to make them, we want to compress them into a super small space and have them all go in this section. So this is what we call cooling. This is super difficult. We basically need to smash them into stuff to slow them down, and then accelerate them, and then smash them into stuff, slow them down, and then reaccelerate them. And we need to do that like 1,000 times in a span of 1 kilometer. And it's really hard because, again, these muons are like decaying in 0.1 seconds in the lab frame, actually less than that. So we need to do this before the muons decay. So there's a lot of R&D work that is going on into this. A lot of people think this can't be done, or it can't be done on the time frame where we think it can be done. This process has been demonstrated. It's been done. Cooling has been done, not to the extent that we need it, but that's why we need R&D for it. All right. The last thing we need to do is, once we have this beam of muons that is well behaved, we need to accelerate it to go really fast. And so there's a number of key challenges here with magnet design, magnet powering. The muons are decaying, so you need to shield the magnets from their decay products, and so the magnets need to be really big, which is hard to control the beam. So there's all of these constraints on the magnet technology and the accelerator design that really require a lot of exciting R&D that people are actively working on. We have a student at Princeton who's working on high temperature superconducting magnets. So normally, superconducting magnets need to be kept at liquid helium temperature, liquid helium temperature, but which is super difficult and imposes a lot of constraints. If we can run magnets at still cold, still liquid nitrogen temperature, but not nearly as cold as normal superconducting magnets, that will be a huge power save and capability save. And so this is a test of one of our students doing on high temperature superconducting, where this copper colored thing is the actual material itself. And this is the smoky stuff is the liquid nitrogen evaporating, and we're running that like high current through it just to measure its superconductivity. Okay, so once we manage to produce the muon beam and collide them, we then have to think about what is our detector going to look like. And the main challenge driving detector here, not accelerator, detector design, is that, again, muons decay. And muons decay into neutrinos, which I'll get to in a moment, and electrons. And these electrons are super annoying because we don't want them there, and they smash into stuff, and they create a huge mess called beam-induced background. So you can imagine these muon beams, they're decaying constantly. We get a ton of electrons, and then the electrons are bouncing off materials, showering our detector. We are all and what's happening, this beam-induced background, these are photons in blue, and this is actually only 0.0003% of a Bib event. So this is truly overwhelming. You can see the calorimeter hits from beam-induced background here on the left, the huge number of particle tracks that are coming out here from a Bib event on the right. So this is truly something that we need to overcome when we're thinking about what our detector needs to look like. So mitigating these copious amounts of backgrounds is really what is driving detector design. So we need a combination of high spatial precision. So for example, Our tracker needs 10 billion channels. LHC detector trackers only have 100 million. Our electromagnetic calorimeter needs 100 million channels. Our current Atlas and CMS electromagnetic calorimeters only have order of hundreds of thousands. And our hadron calorimeter needs 20 million channels. Currently, Atlas and CMS only have like 10,000 or so. So this increase in granularity is enormous. We also need high timing precision. A lot of the beam-induced background particles maybe are early or maybe are late and have different time signature than the particles that are coming from the primary collision point. So the better timing precision we have, the better we are able to discriminate between the background and the particles coming from the primary collision point. And then finally, and this is something that I'm excited about and I'm starting to work on, is we're going to need hardware-driven machine learning algorithms deployed on our detector to actually be able to quickly decide what do we think is interesting, what is signal, and what is background, what is coming from the beam-induced background. Okay. I promised I would come back to neutrinos because I know I have some neutrino enthusiasts in the room. So it's something I'm starting to think about that the particle physics community is really starting to talk about is the synergies that a muon collider can have with neutrino physics. Because remember, muons decay to electrons and to neutrinos. And there could be some really interesting stuff we could do with those neutrinos. But most of the people working on a muon collider are people like a collider physicist like myself. I don't really have expertise in neutrinos. So we're trying to facilitate more discussions and really understand what we can do with this and how we can make a 3-in-1 detector. Okay, so we could potentially have, we have muons decaying kind of earlier before a lot of the acceleration. These produce lower energy neutrino beams, which could potentially have oscillation experiments. For those of you who are familiar with oscillations, can get into that later. But in the main collider ring, where we have these super energetic muon beams, we produce super intense neutrino beams. And that is something that we haven't done before that has interesting implications for things like neutrino behavior at super high energies with nuclear interactions, et cetera. There's also this interesting, I don't need to get into the details, we don't even need to build a custom detector for this intense high neutrino beam because neutrinos coming off the collider kind of skim our detector a little bit. And so we can kind of even get some neutrino detection for free with our detector that we want to use for the normal colliders. And there's physicists thinking about what can we do? How can we exploit the detectors that are already going to be there? Okay, so I think it will come as no surprise that there's been an extreme rising interest in a muon collider program, particularly from early career physicists. So on the left, there was a poll that was circulated to the US particle physics early career community less than a year ago with the question, how excited are you about the physics case of a 10 trillion electron volt, 10 TeV muon collider? And you can see with 1 as not excited and with 5 as extremely excited. You can see of a muon collider in the literature, where gray is all paper and that we feel right now for muon collider. This isn't the first time that the felt such excitement. And so that's why these kind of rises have come, you know, these falls have kind of come after these peaks. And so it's my goal to make sure that this peak does not come with maybe a bit of a slump in the next few years afterwards. All right, so let's revisit our future collider timeline, which of course has an asterisk because I can't predict the future. But we have our LHC running until 2040. We have our FCC, which is CERN's next flagship project, turning on around 2050 with the Higgs factory and turning on the proton-proton future circular collider in around 2070. And on the muon collider side, I'm giving you a timeline that is technically limited. So if we had all the money in the world, all the money, not in the world, all the money that we need to execute our program, we could do this timeline. This is not the case. This timeline will slip to the right. We hope that we potentially can secure the funding so that it doesn't slip decades and decades. So the first thing we need to do is what we call a demonstrator, which is to prove that the technology works, particularly the technology of cooling the beam, of smashing it and then reaccelerating it and then smashing it and then reaccelerating it so we can get an actual beam of muons. So that technology has a lot of fundamental questions and things that need to be proven. That we want to do in the 2030s, preferably in the earlier side of the 2030s. And the earliest we could start to take data with a muon collider would be the 2050s. And so this is something, if we are able to achieve this technically limited timeline, which again might be challenging given certain logistics, we would be able to increase the energy scale that we're currently able to access by a factor of 10, 25 years before the FCC HH, which is something I'm really excited about. Okay, so I showed you once the standard model with a lot of these open questions. So if we want the bounds of our knowledge to be expanded beyond the standard model in, say, the next 25 years, to the time to really get started working on these hard problems is now. So before I close, I want to emphasize that it's not just the early career folks, it's not just me who are excited about a muon collider. In fact, a muon collider has been, R&D program have been endorsed by multiple panels of experts, including this P5 particle physics project prioritization panel that is presented with, that is really the guidepost, the guide of our particle physics project funding in the United States, as well as a National Academy's report that is a little more forward-looking into several decades in the future. And so with the P5 report, as you can see in this quote, even compared to the ambitious goal of constructing and operating a muon collider, even compared this to the 1960s goal of trying to land a man on the moon, calling it our muon shot. And so if we are able to one day achieve a muon collider, hopefully within my lifetime, but it's okay if not, that would truly be one giant leap for mankind. So thank you.